Welcome everyone again, and thank you for joining our evening lecture of Young Seconds. As I see some more people joining us in the room, I will have to repeat some housekeeping rules. There is no fire alarm drill planned for tonight. So if you hear the fire alarm, please exit through one of the two doors and then turn right. The assembly point is towards the end of the street. Tonight, we have invited Atif Rasheed from Imperial College London to give us a presentation on his research titled A New Low-Cost Seismic Isolation System Based on Pre-Inca Technology. This is based on a project that was funded by the Second Fund 2024. Atif is the winner of this award. As I mentioned, Atif is a PhD student at Imperial in the structure section and specifically in the Emerging Structural Technologies Research Group. His research focuses on the development of an innovative low-cost seismic base isolation system with wrapped stones, and this is aimed to enhance the earthquake resilience of developing communities. Atif holds a bachelor degree in civil engineering from Balochistan University of Engineering and Technology and a master in structural engineering from the National University of Science and Technology, Pakistan. And he has been a lecturer for 3 years at the same university. During his master's degree, he was part of a research team that conducted probabilistic seismic hazard analysis, contributing to the development of PGA and SA maps for Pakistan, which were included in the recent code update. His research interests include shake table testing, seismic base isolation, seismic hazard analysis, numerical analysis, and disaster resilience assessment. So without further ado, I will invite Atif to start his lecture.
Thank you, Maria. Thank you so much, and thank you to the committee for believing in my project and awarding me the second Fund 2024. My name is Atif. I'm a PhD student, a third-year PhD student at Imperial College London. Today, I will be speaking about a new low-cost seismic isolation system based on pre-Inca technology. This research is kindly supervised by Dr. Christian Malaga. The theme of my presentation is defeating earthquakes by incorporating naturally and locally available materials. So through this talk, I aim to take you on a brief journey that connects ancient wisdom with modern earthquake engineering. A quick background. Earthquakes are arguably the most destructive of all natural hazards. According to one estimate, nearly 60% of global disaster-related casualties are caused by catastrophic earthquakes alone. However, if we look at this well-famous map, seismic activity is not uniform across the globe. Instead, certain regions are far more prone to earthquakes than others. So one such region is the Andean region, located along the Pacific coast, one of the world's most seismically active zones, where numerous large earthquakes have occurred throughout history. Archaeologists in this region have uncovered some fascinating evidence of ancient construction practices. Among these is the use of shikras, a traditional construction element that predates modern engineering by thousands of years. The word shikra comes from Spanish and refers to stones wrapped in vegetable fibers. What you see here is an actual specimen of shikra dating back nearly 3,000 years, unearthed from Las Shikras, UNESCO World Heritage Site in Peru. So during the late 20th century, numerous archaeological excavations were carried out in the Andean region of Peru, revealing remains believed to be ancient sanctuaries dating back to around 3000 BC. Among these, the city of Kerala, belonging to the North Asian civilization, was declared a UNESCO World Heritage in 2009. And there are other numerous famous sites were also discovered. Remarkably, excavations at these sites led to the discovery of stones enclosed in bags of vegetable fibers, the shikras, which formed part of the structural foundations of these ancient buildings. So according to the findings of archaeologists, shikras commonly placed around the walls of structures, they call them shrines, which were built on raised platforms, which are evident from here. So when new shrines were built, they were constructed on top of the leveled remains of earlier ones, forming stepped pyramids, which shikras integrated into the substructure. So shikras were discovered in large quantities beneath the adobe walls, varying in shape and size, with gravels filling the space between them and the walls. This arrangement not only enhanced structural stability, but also it's also believed that they dissipated seismic energy from ground vibrations. The fact that these structures in the Andean region survived more than 3,000 years ago, 3,000 years, in one of the world's most seismic active zones, demonstrates the phenomenal performance of these shikras. So this was one of the remarkable advanced engineering intuitions of ancient Peruvian builders who, without modern theories, achieved what we today called seismic isolation. So this realization actually inspired my PhD research. Can we reinterpret this ancient technology using modern analytical and experimental tools to develop a low-cost seismic isolation system for developing communities? To further validate this ancient wisdom, researchers have carried out a few modern studies replicating the behavior of shikras under seismic loading. One of them was carried out by Professor Newman. They conducted a shake table experiment using a rammed earth model and modified shikra isolation to study its seismic performance. The system consisted of a modified form of shikra, which was 3 layers of river stones and wooden beam, which are evident from here. The system was subjected to a 1970 Juarez earthquake, and the study found that the low-cost shikra-based isolation system effectively dissipates seismic energy. And one of another very important study was conducted by Professor Fukuyama in Japan. They conducted small-scale experiments on models inspired by shikras. This layered shikras model evaluated the reliability and fundamental characteristics of ancient earthquake-resistant method. Their investigations involved different factors, including the number of layers, randomness, dead weight, and interstitial sand. The results consistently demonstrated a significant reduction in seismic response acceleration. So this was observed a distinct acceleration plateau atop the shikra base when input acceleration surpassed a specific threshold. So his observations revealed that these units exhibit a rolling seismic isolation mechanism, a distinct motion characterized by combined rocking and partial uplifting, leading to seismic energy dissipation. So building on these ideas, my research revisits this ancient wisdom and attempts to formalize it through modern mechanics and computational models. So in this study, the proposed application of Shikras targets low to medium rise structures. The concept is to place the Shikra units beneath the load-bearing elements as illustrated in this 3D rendered schematic. To understand their mechanics, we begin by simplifying the system into two-dimensional planar representation, one that consists of a single, maybe a masonry wall resting on a plinth beam supported by a layer of shikras with the foundation system. So building upon Professor Fukuyama's findings earlier in sites, where energy dissipation occurs through rocking and rolling. So we idealize each shikra as a regular polygon, specifically an octagon in this case initially. The superstructure above is represented by lumped mass, and the interface friction between shikras and base is assumed to be sufficiently large to prevent any horizontal sliding of these shikra polygons. So once the ground acceleration exceeds the threshold, the shikras begin to rock about their pivotal points, and due to this impact, the energy will be dissipated, and this is how the energy dissipates, and the ground excitation coming from will be reduced. So to describe this motion analytically, we first examine the geometry of the idealized shikras. The polygonal body is defined by two key parameters. One is the number of sides, and the size of the polygon, which is inscribed in the in a circle. And one of the most important geometric property is the angle, which is this phi, defined as an angle between the line joining the rocking vertex, the rocking vertex to the centroid, and the vertical through that vertex. So here you can see the motion of a single shikra subjected to ground acceleration, denoted by U double dot G. Every geometric property, including phi, the side length, and the lever arm, can be expressed as a function of n and the size r. So depending on whether the shikra rocks towards left or right, the motion can be described by clockwise or anti-clockwise angular displacements. So this distinction forms the basis of deriving the rocking to the left and rocking to the moving to the right forms the distinction between developing two distinct phases of motion. So since the system exhibits rotational motion with changing contact points, the Lagrangian framework is ideal for describing the dynamics. The motion satisfies the Lagrange equation, and this is the simplified form, and hence we can employ variational principles to obtain an analytical expression to describe this equation of motion. So the corresponding Euler and Lagrange equation is formed, and we have a very sophisticated kinetic energy, which is dependent on the rotation. And then if we observe here, due to this rotation, we have horizontal and vertical displacements. And we can develop empirical expressions for these horizontal and vertical displacements. However, so once we do some differential calculations, differential equations, we obtain this very famous equation, which is the rocking equation of the rectangular block. But here, the distinction is the frequency parameter P, which differs significantly. So it represents geometrical inertia property rather than the natural frequency of the system. So this parameter P depends on several quantities, the characteristic size R, and the mass ratio of the mass superstructure of the mass and the number of Shikras and this mass ratio. And then the most important, again, one characteristic is the I naught or rotational inertia. So once we have these parameters, then we can look at the analytical expression. So we can easily develop an expression for this rotational inertia, and then when we substitute it, we get our complete expression, which describes the motion of that block to the right and to the left in both systems. And one can argue that the Shikras are irregular, we can incorporate Green's theorem, and which leads to the shoelace formula to develop an expression to determine these geometrical properties of the irregular system. So for this purpose, the geometry of Shikra is first to be drawn in a CAD. From that, we can export the DXF file, and then we can extract the vertices, and we apply the Green's theorem, and we can obtain the geometrical properties, including the centroidal inertia, with very precision. So now this enables us to obtain the mass moment of inertia, and then thereby we can extend the analytical model beyond idealized symmetry. With all these parameters defined, the next step is to determine the minimum base acceleration required to initiate the uplift, the activation of the isolation or the seismic isolation. So here we have obtained an expression which states that the critical acceleration or the activation threshold can be derived directly from the geometry and turns out to be independent of mass. So instead, it solely depends on the angle phi, emphasizing again how pivotal this geometrical parameter is. So this figure shows the physical meaning of phi, that how it governs the onset of rocking. So our computational workflow is the analytical model. It follows an event-based process. So we begin the geometry initial conditions, the excitation input as the motion evolves. We identify when uplift occurs, and then we solve the equation of motion, and we can obtain we integrate this theta over time. And during this simulation, the model continuously checks whether the polygon has rolled over to the next pivot. If it does, new initial conditions are established, accounting for energy loss during impact, and then the process repeats. So if not, the system continues to rock about the same pivot. This sequence continues until the excitation ends or the motion ceases in this case. So initially, if we look at the number of sides, if we increase the number of sides of the polygon, that the critical acceleration reduces. So which is very intuitive in a sense that as the number of sides increases, it becomes more and more circular. So the more circular it becomes, the more easier it gets to rotate or pivot to the next point. Here on the right, this plot represents the maximum rotation attained by each polygon under identical pulse amplitudes. So we can see as the n increases, the maximum rotation decreases. And initially, because the pulse we are inputting here is 0.35 g with the amplitude, and the critical acceleration for the polygons with sides 8 and 9 are below this. That's why there is no any rotation in that case. So here we can see that how when it decreases or it becomes more circular, it becomes more favorable in a sense that it favorable outcome for isolation. As for high N, A critical approaches approximately 0.05 G, suggesting it excellent energy dissipation even under small excitations. So here we examine the rotational response of different polygons. Yeah, so we can see here, maybe if I Yeah, so as we discussed earlier, that when the polygon has 8 regular sides, there is no rotation, and when the sides increases, we can see that how the initial uplift increases and the maximum rotation of that polygon also increases. So it means that when the maximum rotation is increasing, there are more impacts, and the more impacts means there is more energy dissipation. So we can look at this if we have, for example, a polygon which has 50 sides, which becomes more capable to dissipate the seismic energy. And here, this slide shows the time histories of rotational displacements, angular velocity, and angular acceleration of sine pulses with fixed amplitude. The amplitude is 0.35 g, and a fixed frequency, approximately 1 second period. The results are shown for polygons ranging from 8 to 50 sites. You can clearly observe that n increases, the angular displacement reduces, and the motion becomes smoother. And the impact induced spikes in acceleration, reflecting increased rolling and reduced impact intensity. Here we represent a dimensional representation of the acceleration response. The y-axis shows here the absolute maximum acceleration normalized by p square phi. P is the frequency parameter, while the x-axis represents the frequency ratio. So this normalization allows us to generalize the results across different geometries and sizes. So the envelope becomes more distinct as n increases, which is very evident from here. And so it means that higher sided polygons exhibit more stable and predictable behavior. Then we observed at the rolling spectra, and that how these contour plots display across variation excitations. So the excitation amplitudes ranging from 0.1 g to 0.6 g, and frequencies ranging from 0.1 to 10. So on the vertical axis here we have the ratio of acceleration, which is again normalized, indicating normalized rotational amplitudes. So each plot corresponds to a different polygon, starting from the 8 and then eventually finishing at 50 or 48 sided. So here we can see that as we increase the number of sides, the maximum rotation is decreasing, means the horizontal displacement is decreasing, and there are the horizontal displacement is decreasing and the impacts are increasing, which means the energy is dissipating more frequently. So in parallel, we are developing a hybrid numerical framework as well that combines the strength of just 1 minute. Yeah, so this combines the strength of discrete element and finite element method, because as we it can be seen that these chakras are more discrete elements. So it would be better to go for an approach that uses the strengths of some softwares, which are, because every software is not strong in every dimension or every that's why we chose this, that we can go for to select the discrete elements in a framework of DEM. Here we are using an open source software which is called YADE. YADE is an acronym for Yet Another Dynamic Engine. So the discrete elements or the chakras are modeled in a discrete element framework of YADE, and the superstructure is uh, modeled in FEM framework of OpenSeas, and then they both are integrated, which is called multi-platform numerical hybrid simulation. So this works initially there is an integration module and there is a substructure module. The integration module from the superstructure applies some ground displacements or any displacement. That displacement is transferred to this the substructure module, maybe in discrete element, which applies the forces, which applies that actually displacement, and in return it produces the forces which are provided to that integration module, and then this cycle continues until the ground excitation or the any pulse that finishes. So we have very basic. We have conducted was an initial investigation. Sorry for this poor rendering of YADE. It is not very strong in rendering. So we can see our initial investigations in this framework are promising, that the frequencies at the so the responses at the top are decreasing. And so beyond this numerical, we are also conducting an experimental numerical hybrid simulation campaign, is also under preparation in collaboration with University of Toronto. Because the aim and purpose of this campaign is that shake table experimentation are very resource exhaustive in terms of time, in terms of maybe financial resources. So it is hypothesized, or it is very convenient if we have one critical member to be experimentally investigated and the other members or the other part of the structure is numerically modeled, and then we can integrate these two substructures, and then we can look at our system more in a better way. So here what we can do here, that we are planning to develop the experimental or the chakra based system in an experimental or physical substructure, and the superstructure will be modeled in OpenSeas, and then these actuators will be used to apply these excitations, and the interface or the communication between these two substructures, the experimental substructure and the numerical substructure, will be carried out through Nikon, which is network interface controllers developed by Professor Kwon in University of Toronto. And here we have conducted a very initial substructure module. Actually here both the substructures, the physical and numerical, initially both are modeled in OpenSeas. So just to get the Nikon or this communication tuned in a way that both systems can interact like in a way that we want them to interact. And here this is a very basic study of the results of this single degree of freedom based isolated structure, in which we model the same in one as a standalone model, and then in a separate model we subdivided the both parts, and they communicated through this Nikon, which is the network interface controllers, and then we can see that the results are almost similar. So with this I conclude. I leave these for you to read. But I could say that this research revisits an ancient Andean construction technique and reinterprets it through the lens of modern structural mechanics. The analytical and experimental results demonstrated the potential of shikras as an effective, low-cost isolation mechanism, particularly suitable for low to medium-rise structures. Thank you all for listening. I would be very happy to take your questions.
Thank you very much, Atif, for a very interesting presentation. And now let's open the floor to questions, either from the people in the room or for the people online. Please type in the chat or just unmute yourself and you can ask. So let's start with the room first.
Thank you so much. What's the rope made of, just for interest? The rope that holds the stones together.
So the rope that has been explored or been found in the shikras, it is vegetable fibers. So here we are exploring different options that how to make it more durable, that can sustain loads and it can sustain for long periods. So maybe we are exploring that we can use some steel fibers or maybe some vegetable fibers or fibers made of those nylon things.
And what was the size of the ones that that were in place in real life? How big were they?
So the uncovered shikras are 20 to 40 centimeters in diameter if they're rounded.
And so they looked, the one that I think you had a picture up of, ones that were 5,000 years old?
Yeah, almost 3,000 to 5,000 years old, yeah.
Interesting, and they looked pretty intact. So the design life looks...
Yes.
So then just a question on how are they constructed? Is it a certain type of rock that they were using, and is there like I'm just thinking because a lot of Inca structures are quite amazing. So I'm thinking, did they use these to possibly roll things into place, or I'm just thinking generally speaking.
This is a very interesting question. This is what I was referring, that ancient wisdom of the Peruvian builders. So they were very amazing. Those actually I have not been to the site of the Peru to explore the Shikra myself, but I believe that the construction type or the number of stones placed in one shikra element, that is the more fundamental part.
Very good. Just a final question is, this is one ancient technology that many of us, we would have forgotten about. And semi-recently, there was an earthquake in India, and a lot of people unfortunately died in the concrete structures. So I'm just thinking, are there any others from your research or from your community, any other ancient technologies that we could start researching more that come to mind other than shikras, please?
Yes, I came across, there was one technique in Iran. And there is a I don't exactly remember the name of the it's a tomb of one of their leaders. So it is made in such a way that the two parts of the structure, they are they act in different ways when there is a seismic activity. And there is the structures in Greece. We have seen them, so they have been standing for very long time, and again the Greece is very seismically active, so people and the researchers are looking at those structures as well.
Yeah, I have a question, Atif. Very nice presentation, thank you. I was wondering, how do they compare these shikras compared to modern base isolation in terms of seismic performance? Like the reduction in acceleration and so on in the superstructure from, let's say, a modern base isolation solution to these shikras. Have you?
Actually, they are an alternate to seismic-based isolation in a way that the conventional seismic isolators, they work in a way that they use dissipating materials within them. And here, and they slide. For example, we have curved isolators like triple pendulum isolators. So they slide, and based on that they reduce their energy. Here, it is the seismic energy is reduced by the motion, but the performance compared to those, I have not yet explored it. So it's again a way that I can look at it, that how if we apply this same thing in a conventional way, that how these shikras can reduce the seismic energy.
Okay, and another question with your analytical solution. So you had a number of polygons. Were they all rocking the same amount, or was there a difference between the rocking of the different polygons?
Yes. So initially, this is one of the idealizations of our analytical model, that when there is a base excitation, all the polygons, they behave similarly.
Okay, but I'd imagine in a real structure it would be
Yes,
very
so
random
exactly. And that's why we are looking more into our experimental part, and then we can tune our analytical model more according to that.
And I was also wondering, in the YAID, the numerical analysis, was the rocking uniform throughout the polygons or the idealized shikras, or was it different?
No, yeah, it is different. So the initially the load is being uniform on all particles, but still the behavior of each element was not very similar to the other ones. So it was different.
And another question, if nobody wants to ask. So as the number of sides increase, then it seems that the performance improves. But then it becomes circular. There's less friction, isn't it, with the base? I'd expect that it will just slide through without better rocking.
With more sides, it apparently looks circular, but it is more like a saw. So it is more jagged.
Okay.
So because of that, so the friction increases, and the more impacts, the more energy dissipation.
Okay.
Hey, congratulations for the presentation. I have a question is regarding the superstructure. Do you have any idea so far of if there is any range of period for the superstructure? I mean the natural period for which the isolation system is more effective?
That's a very interesting question, and I have not yet looked at this. Initially the target is from low to medium rise structures, maybe 2 or 3 story structures, because our focus is more to the developing communities. So this is a very nice area that we can look at it, how for which specific period of structure we can explore it. Thank you.
We have a couple of questions online. First, there is a question whether this research work has been published by Asal Hussein. If you have published this work, if there is a publication.
Not from us, so it is under publication, so not yet formally published.
Okay, and then there is a question by Mahina. How will they behave on slope in case of hill buildings?
In case of?
If there is building a hill.
Oh, that is very interesting. Yeah. So it needs to be explored that how it behaves. It's again a very nice idea. Yeah. So we have not explored it. We can look at, but apparently it looks that we have to make the base horizontal to make them to be effective, because otherwise, and then we have because these are again we have to restrain the horizontal movement as well, otherwise it will there will be a huge residual permanent residual deformations.
Great. And then there is a question by Sasan. Can you please tell us more about the hybrid simulation test that you're going to do?
Yes, so the hybrid simulation test, it is under the process, so it is very at the initial stage. Hybrid simulation, so we are planning to conduct the experimentation part at Imperial's structures lab, and then we will be using the University of Toronto's Professor Kwon's developed framework, which is network interface controllers. So we will be publishing it very soon, or then we can see, you can see it over there.
Great. And then we have a question by B. Bark. In your model, shikras are taken as rigid polygons with high friction, but in reality, energy comes from stone-to-stone friction within shikra. Have you modeled this internal friction in your model?
Yes. I have two frameworks. One is the analytical framework, one is the numerical framework. In the analytical one, we are assuming the shikras as very rigid. But in the numerical framework, the vertical, there is possibility that when there is applied load, they are not as rigid as we are assuming them in the analytical model. So yes, we have considered them in our discrete element modeling, and that's why they have indicated good result.
Okay, and one more question by Asal. What about the rock specifications in addition to the size? And can you just use available resources?
Regarding the size, so we are sticking to the sizes which were uncovered, the range from the diameter of one particular shikra from 20 centimeter to 40 or 50 centimeter, and it was observed by Professor Fukuyama and in his observations as well, that if we increase the stackings, so the energy is more dissipated.
Is there any other question from the audience?
Yes, I have a quick question, and then I'll pass over to you. It's kind of similar to what has been mentioned in one of the questions online between this friction inside the shikra. I was thinking more of the different polygons hitting each other, and that will cause some energy dissipation. So was that considered?
Yes, yeah.
Okay.
So the interaction of the one polygon with interfaces, top and bottom interfaces, and then when there is any contact between two shikras or any polygons, spheres, then there is energy dissipation over there as well.
Okay,
yeah, so this is considered in the numerical framework, but not in the analytical framework.
And then the assumption is always that the shikras could always carry the vertical load. Is there a point where they are damaged that?
No, because no. So I think we at this stage we believe that they're strong enough to carry the vertical load.
Okay.
Really good. Just a question about in the testing, when the movement was occurring,
Uh-huh.
was there any of this kind of movement as well, like differential settlement?
Actually, we have not done testing yet.
Yes.
So the hybrid experimental campaign is underway. So we have not explored it yet. So we have to make sure that there is no any like settlements on either side. So the superstructure or whatever the structure is, it should remain horizontal. Otherwise, if there is settlements on one side, then it will definitely produce and develop or some local failures. So that will be kept in mind.
I understand. And so in the shikras, you said it's the number of rocks that you put inside that's important. I was just wondering, what size are those rocks inside, and are they angular? Are they like
Yes, so we are so we have not performed experimentation. So until this stage, so the whole shikra element is considered just one size. So when we perform some experimentations, then we will evaluate these parameters, that what number of stones should be placed. And so the idea of our study is to develop that eventually, because so that develop some scientific principles that can be adopted to be applied in practical.
I understand. And so in your experiments, I saw that you've got a hard surface, then you've got your shikras, and then you've got the superstructure, the foundation of the structure. The structure is like a raft, so that the load will, but I'm just thinking, the bottom, in practice in Peru, what did they have on the bottom to make it a hard surface?
Actually, they in archaeological excavations, so it is just, so what they did, initially they put these shikras, and after some times they build on top of that shikras. So those shikras maybe acted as the strong layer for the upper ones. So in our case, we will be putting some like lean concrete, strong concrete, so that the foundation maybe it gets strong, so there's no any local or settlements due to those when there is any vertical gravity load.
Very good. I just want to say, I wish you the best. I hope you save a lot of people's lives.
Yeah, that is the aim. Thank you very much.
We have one more question online from Peter. In reality, the stones beneath the building are interlocked through geometry and friction, and the upper foundation slab does not roll as assumed in your model, isn't it?
Actually, so because they are not fixed permanently, that's why the movement of the superstructure and the foundation, it is very distinct and separable.
Is there any other question from the audience? So is there anything more from the people online? I think I can see something on the chat. Yeah, okay, so there is one more question. In India, we have Kanikuti, Himachal type, Ikra, Assam type houses, which are ancient vernacular architecture, but they behave seismically better compared to concrete or masonry houses. But this shikra is more base isolation based. Yeah, I think this is more of a comment rather than a question.
Thank you.
Great. So thank you everyone for joining us, the people online and the people in the room. Thank you, Atif, for an excellent presentation and sharing your recent work. And for the people in the room, we have a networking reception upstairs in the members area. Thank you all again, and have a good evening.